Okay. So Friday, we finished off. We were talking about all of the applications of physics, how we break down physics and engineering problems. Most of it is going to be following, at least the way I do it. I like to follow the techniques we were developing with these volume problems, namely as starting off things as just generic differentials. Work is the integral of dw. Very easy to at least get started, but it helps us kind of guide our brains towards understanding what do I mean by dw. We mean the infinitesimal amount of work done with however we want to slice up and break down the system. And so in most situations, we write it as the force times dx, because our basic physics law, work is force times distance. And so an infinitesimal amount of work, we cut up our distance infinitesimally, and we have a variable force depending on where we are at on that distance scale. Sometimes, though, I like to break up the force as df, where we're changing the force. The force changes on each piece of the system, and the distance doesn't play as big of a role. It changes linearly. So we'll see this potentially in hydrostatic pressure a little bit, as well as these rope pulling problems. So we ended, I think, introducing Hooke's law. So the first example for non-constant forces, something fairly basic. We're stretching a spring, and we have a spring at 10 centimeters, whereas its natural resting length. Hooke's law states that the force on a spring is proportional to the distance we stretch or compress it. So the distance changed from equilibrium. So we have a spring constant, k, that is our constant of proportionality, and then x, of course, is just the distance from equilibrium. And we're given information like to hold a spring at 15 centimeters requires 40 newtons of force. How much work is done stretching the spring from 15 to 18? So on Friday, we started our work equations. Work, integral of dw, integral of f dx. And if we wanted to, we do know the bounds. Since we are given hard bounds, the distance we're stretching is between 15 to 18. So we can go ahead and fill in our law. We know that the force follows kx, and our distance, oops, I put an extra x there. We just want dx from 15 to 18. So we could do this integral. Of course, we need to actually find k. So how do we find k? K we find by the first piece of information. So we could do that first. You could do it at the end if you want. We know that to hold the spring at 15 centimeters requires 40 newtons. So $40 newtons is a force. K is our constant we're looking for. And x, remember, is the distance from its resting position. So its resting position was 10, and we stretched it 15 centimeters. So of course, we're stretching it 5 centimeters beyond its resting position. Our K is then 8. And if we wanted to give a unit to that, so 40 newtons, these are both we were in centimeters, I believe, yep. So we will have newtons per centimeter on the units for K there. So our total work, integral of 15 to 18, 8 x dx. And so, of course, we get 4x squared from 15 to 18. So 4 times 18 squared minus 15 squared. Whatever that is. I don't have a calculator handy. 15 squared is 225. Anyone know what 18 squared is? Was it like 400 minus something? I guess it's like 3 something 4. Anyway, complete that calculation. And that will be our total work. One thing we should check if we want is the units. And so the 8 had newtons per centimeter. And so the work done when I plug in these 18s and 15s, it'll be centimeters squared. So the overall units will be newtons times centimeters, which is a weird unit of work. Newton meters is a joule. Newton centimeters is, a tenth of that. But it is a proper unit of work. Any questions on that one? Good. So let's get into
in the equation. Sorry, in the equation, doesn't it start like the coordinate system technically starts at 10, and so shouldn't it be from 5 to 8? Or am I thinking about it wrong? Like in your bounds.
I see. I might be wrong. Let me think. Since we want x to be the displacement, yeah, you're correct. Thank you for that. I'm catching that. That'll make the computations a lot easier.
Oh, I have a quick question.
Yeah.
So when you solved for k, how did you get that 10 centimeters?
10 was the resting position.
Oh, okay.
Yeah. Yeah, so the work done, we're not actually stretching it 15 centimeters beyond where we were at. We're stretching 5 centimeters up to 8 centimeters. Everyone catch that? So the correction was, since our origin, we need to essentially place our origin at this 10 centimeter mark. And so if we were to really draw the picture, even though I have a spring that's 10 centimeters, we want to place the origin at the natural resting position from the spring. And so when we are here at 15, or here, I guess we should say, our position is 5 centimeters, which gives us a stretch of 15. And then we want to go from there up to 18. And so, of course, we get the same thing. Nicer numbers now. And then we can actually compute that. So 64 minus 25 is 39 times 4 is 156. Yeah. Did I do that right? 39 times 4 is what? 120 plus 36. Yeah. So newtons times centimeter. Okay. So let's get into some more difficult work problems. And the first one we're going to take a look at is going to be pumping water out of a tank. So you'll see these problems a lot. They appear a lot in Calc 2, whether it's applied math or math department. We've got, I'm just going to go ahead and draw the picture. We've got a right circular cone of radius 4 meters and of height 10 meters. It's filled with water up to 8 meters. And what we want to do is we want to find the amount of work done pumping the water out of the tank. So pay attention to the words. A lot of these types of problems, we would almost give you the picture. Sometimes they're hard to visualize if we just kind of explain. It says something like a right circular cone, inverted, has base radius 4 meters, height 10 meters, is filled with 8 meters of water. And then, of course, we want to find the work done pumping the water out of the tank. So one of the key points here is the work is done against gravity. You see a lot of these types of examples. Anytime we're lifting anything, raising anything, pumping something out of a vertical tank, the work that's done is we're doing work against gravity, meaning I need to push things upward. And so the way we want to slice this up and understand how each piece contributes to the work, we want to slice perpendicular to the y-axis. So maybe some steps in word problems. Draw a picture. I would recommend defining an axis, define coordinates and variables. So in a lot of these problems, especially since they are now real world problems, we don't actually have our coordinate systems yet. So we want to impose a coordinate system on it to make sure we are consistent with everything. Natural coordinate systems, sometimes you could put one at the top, bottom, or the water level. Depending on where you put it, you can always get the right answer, but I always think it's helpful to define your coordinate system at the beginning. So that way, otherwise sometimes you work out a problem and you can confuse yourself as to where your coordinate system is at different points in time if you weren't kind of clear on that from the beginning. Let's put our coordinate system at the bottom here. So our origin is here, and our variables, let's just keep our standard X and Y variables. So that this distance here is Y. We want to use our vertical axis because we are doing work against gravity. And so now what we want to do is once we have our variables, we want to determine, in this case, let's say equations, which I'll put as physical laws. In Calc 1, these are often constraint equations in optimization problems. So we want to determine the equations and physical laws relating to variables. So how are we going to set this up? What is our work done? Let's talk about these physical laws. We're breaking our work down into infinitesimal slices of work. And since we are pumping against gravity, the direction of the force has to be perpendicular to the, or excuse me, the direction of force has to be parallel to the direction of travel in order to contribute to work. Namely, any piece of water here like that, if it moves sideways, it's not contributing to work. There's no force pushing left or right. So any left and right forces, you're kind of given that freely. You can kind of think of it if you're pushing a box on a frictionless surface, you're not doing any work. You can literally just push the box and it'll go. The force is downward from gravity. So to do work against that force, we have to go against gravity or with gravity. So work can be done by gravity or against gravity. And so we want to cut up perpendicular to the y-axis, because in doing so, on this entire disk, the force required to pump out this part of the disk versus the center of the disk versus maybe the edge of the disk, it doesn't matter, even if they have to move horizontally, right? Even if the spigot or something was like over here on the side, putting this piece of water over here and having to push it sideways and then up and then out, only the vertical component is going to contribute to the amount of work. So we can treat these disks sort of as whole, and then the whole effort moving that disk upward is going to be that contribution of work. So how are we going to break this down? Our dW is going to be our force times our distance. And let's write it as dF. Since each of these slices is going to have a different amount of force on it due to gravity, and that force is going to change with different slices. And then we need a distance. So let's actually call it S here. And we will label that as our distance pumped. Going to be related to our variables we've defined. And so this is part of this process of relating the variables. Sometimes we have to introduce a new variable when we start to do this because we realize maybe we haven't had enough. This one's easy enough. Well, if the entire height of the tank is 10, then the distance we have to pump something out, if a disk is sitting at a coordinate of y relative to our system, how far do we have to pump it out? 10 minus y. So that part is easy enough. And now I don't have a differential yet. We should expect a dy coming in here. Our differential is still df, I guess I should say. And so we should expect a dy come out of this df. And so let's break down what this df is. And let's see, I don't know how many more steps we'll need. I think usually there's about 6 or 7 in my Calc 1 breakdown of these. Calc 2 problems are a little bit different. So let me see, let's put scratch work. Maybe we just keep going. What is our df? Df, we'll see this a lot. The force on an object is just going to be the density times the mass. So objects have mass times the force of gravity. Oh, sorry, I should have gravity. Excuse me. Mass times gravity gives us the force on each slice. So this should be a G here. And then what is the mass? The mass is the density times the volume. And so gravity and density are both constants. We'll talk about those at the end. And then, of course, we have this dV now. And look what we were at. We are at essentially a cylindrical problem. So it looks like a volume of revolution. What is our dV with each of these slices? It is this volume of each disk. And of course, we can see the thickness of each disk is our dy. Our dV, this we actually have to determine by our geometry. In this case, we do have a right circular cone. We can change the shape of the tank though. And so that's where a lot of the work comes in. We've got to use these geometry skills we've been building up in the previous sections and now tie it in with all this work and physics laws. So our dV is going to be pi r squared dy. So I'll go ahead and move the dy there at the end. And our last step, well, we need something for r in terms of y. So how do we do that? Let me go ahead and use our list here as our scratch work area as well. We'll put extra steps. The remaining steps after this is the bulk, as we can see. Determining the equations, doing all the variables, applying the geometry, which of course will introduce new variables. The bulk of the work and then the remaining steps are usually integration techniques and solving. So what is our R? Let's break down our picture a little bit. We had 4 centimeters and 10 centimeters. And so at some given height, let's put this in red or orange. Our height y, we need to figure out what the radius is. You see this a lot with triangles, with anything whose cross section is a triangle, vertical cross section, that we can use similar triangles, namely that the ratio of the radius to the height is going to be the same. It's always a constant. And since we know that the radius of the bigger triangle to the height is 4 to 10, we'll have that same ratio, meaning if we multiply by y and then solve for r is going to be 2/5 of y. And our last step, or last big step, I guess I should say, is to plug that in. I'm going to go ahead and pull out the pi as well. R squared is going to be 2/5 squared. And this is our integral. So what do we want to do next? Let's go ahead and get a new piece of paper, give us some space here. We've got 4 out of 25. Gravity times density times pi. So our fourth step would be determine the bounds and integrate. So the bounds, really important for these ones. And this is why I really emphasize defining a coordinate system right after you draw the picture, because it's really easy to confuse where the bounds lie if you're not really clear on how you're defining your variables and in which direction they're going. Sometimes people will do these problems and put their coordinate system up here and sort of invert it, where they consider the depth going downward as positive. You can do that, And you have to be clear with how you're defining it, because the bounds are going to be determined by how you define your variables. So the bounds are always where the slices lie relative to the coordinate system. So our coordinate system here was 0. Where are we taking slices from? From 0 up to 8. And so you can kind of see, another thing you can kind of think about is like, how have we encoded each piece of information in this problem? Does my integral contain each piece of information? The height of the tank and the depth of the water is encoded here, right? That 10 height of the tank, depth of the water. The cylindrical shape was encoded by the pi r squared. Of course, we've got some constants for gravity and density, and then the actual depth of the water, which was different from the entire height of the tank, we have encoded in our bounds of integration. So that's about it. I'll leave the integral to you guys. One note on gravity. I don't know if we will require you guys to know this. I doubt it. Gravity is 9.8 meters per second squared. Most of these problems, I like to keep gravity as gravity and just keep it as a constant g, and keep your answer in terms of g's. Treat your g's just like pi's, right? Pi is, if we wanted a decimal approximation, 3.14. G, a decimal approximation, is 9.8. Again, using these constants in problems just adds to the computational power, but doesn't actually give you anything more. Density of water, at least as scientists, everyone should know. It's an easy one. In the metric system, the density of water is 1. Cubic centimeters per gram. Right? So you hear this in the medicine a lot. Anytime they say 1 cc, I need 1 cc of insulin or whatever it is. It's 1 cubic centimeter, also means a gram, 1 gram of that. And so you might have to change these. I think, where are units in centimeters or meters? I think they were in meters. So multiply that by, your centimeters by 10, and you'll get 1,000. Wait, sorry, I'm putting those units upside down. 1 gram per centimeter cubed. And so it's, do the conversions on that for kilograms per meter if you need it. I think it's, metric system, it's going to be a factor of 10.
Can you go back to the bottom of the other page for like a second?
Sure.
Okay, great. Thank you.
Welcome. Okay. So this was a water pumping problem. Let's take a look at some other ones. Again, we're going to have these constants show up in quite a bit. Let's see. Do we want to do hydrostatic pressure? Yeah. Let's take a look at hydrostatic pressure. Okay, so our example is going to be, we've got this trapezoidal dam. that is 50 centimeters, or excuse me, 50 meters over 30 meters at the base, and a height of 20 meters. And let's see, do we want the water all the way at the top? I believe we do. Nah, for water level is 4 meters from the top. So here's what we're going to do. We've got our water. It's 4 meters from the top, so it's 16 meters high. And what we want to do is find the, let's call it the hydrostatic force on the dam. So what is hydrostatic force? Where does it come from? Well, I'm sure everyone's familiar with the concept of the deeper you dive, the more water pressure there is. Of course, we're in Colorado, so the air pressure here is not as high. So the sort of deeper you are in a fluid, the more force there is of that fluid pressing on you. Where does that force come from? Well, it comes from gravity. So if I am down here in the tank, all of the water that's above you is pushing downward from gravity. And so that is the pressure you feel. Now, the thing is, though, that the pressure you feel at that depth is going to be the pressure you feel essentially from all sides. So in some sense, you kind of think of it as like as a little block or a gel block. If you try to push down on it, what's going to happen? It's going to start pushing out the sides. Right, like the think of the hydraulic press channel or something. If you've seen any of those videos on YouTube, every time you try to smash something, it's going to come out the sides. So even if you're against this wall here, against the dam, the water that's pushing downward here is also going to create a force on the dam. So that's essentially where the force comes. And so knowing this, we can actually divide things up and compute the total force on the dam from what the water will be pushing. And so the force for a given slice is going to be, let's write it this way. Let's get our guides here. We want the total force, the total pressure is the integral of dF, which is the integral of the volume essentially above it, the mass times gravity. So it's going to give us the gravity times the amount of mass times, if we wanted the volume, it's going to be times the depth. Which is going to be the density times gravity times the area of each slice, and again times the depth. So we're getting a little ahead of ourselves. Let's go through our steps and define our variables and define our coordinate systems so we can formalize this now a little bit better. Where do we want the origin? Two natural places. We could either put it down here or we could put it up here at the top. Either way we want to do it. Let's see. We did the last one at the bottom. Do we want to do this one at the top? So I think the book and the way other people will do it is to define the origin at the top, and you can actually define your variable, your positive depth, as going downward. For me, that's always a little awkward because you're orienting your axes slightly different. Though we can do it that way if you guys want. Any intuitive way jump out at you guys? Or how do you guys like to orient these? Any instincts from Calc 1?
I'd probably say with the origin at the bottom.
Yeah,
So-
I agree with that.
Yeah, that
That's always
doesn't
where I
make
like to do it. Origin at the bottom, the only weird thing is like the depth, but that's not actually that weird. It's fairly easy, right? In the last one, it was just 10 minus y. So for me, that's where it's intuitive, but I know a lot of people like to put it at the top. I always just find that if I put it at the top, sometimes because the orientation, if you change it, it can be a little wonky, where if you count your down as positive y. So let's keep it as we did the last one then. And so our y is going to be the distance from the origin upward. So finding relations on our variables. Let's pull up the density and gravity. The depth now, pretty easy. If our height is at 16, or the total amount of water height is at 16, and any given slab, any given slice is at a height of y, then the depth is just 16 minus y. And then, of course, we got to figure out what our dA is. So the dA is going to be given by our width of the slice. So we may want to introduce some extra variables. And we can call the width W. Of course, our thickness of the slice is just dy. How do we find W? Couple different ways. We could just do it using some basic geometry. We could try to use planar geometry. Thing to remember is that this any trapezoid is essentially a triangle, right? We can extend that and it will still be a triangle. So we can kind of use similar triangle techniques to break that down. Or we could come up with the equations to break that down if we wanted to sort of come up with the equations and the slopes of these lines. We assume that it is symmetric. Of course, I didn't draw it symmetric. So let's do a little bit of geometry. I'm running out of space here and redraw our picture. Since we're doing geometry, I'm going to cut this up into ways that we can use triangles. So the top was 50 centimeters. I'm going to break it down as 10, 30, and 10 because we know that our height was 20. And so now we can use all this similar triangles to break down an equation that relates the height that it is above our origin and the width. So what's the slope of this line? If I go up 20, we go over 10. Slope of this line, if I go up 20, we go over 10. Is so 20 over 10, of course. This slope, if we want it to be proper, it'd be -2. So sort of the quick way to do this is if I have this bar here and I go up here, let's draw it out. So our width, we have a length of 30. And then if I go up 20 or up Y, this side is going to shrink or going to grow half of that. And then this side will also grow half of that. So it's essentially 2 times half Y. Or so 30 plus Y. No, 30 plus half Y. Everyone catch that? I was kind of doing some geometry there in my head. I didn't do it too formally. So you kind of got to think, if we start with 30, and then how much is the width going to grow if I go up Y? Well, this piece will grow half Y. And then the other piece should grow half Y as well.
Can you also say, since like trapezoids, if the bases are like the same width, or like if the bases remain the same and your height is the same, it doesn't really matter like how much the bases are shifted to one side or the other. So could you say it's like an overhang of 20 and then a right angle on the side? It's kind of hard to explain, but then you kind of can see the slope more clearly.
Yeah, I see what you're saying. We could do that. I was trying to do some slope geometry. Of course, the other thing you can do is, if you want to do it formally, is, and of course, so this height is 20. And so, yeah, these two heights are the same. Yeah, so we should have 1/2 plus 1/2 here. So the way I was thinking about it is, on this side, the X value grows half the height, the width of the Y. So if we go up Y, we're adding half a Y on that piece. If we go up Y, we're adding half a Y on that piece. The other way, as suggested, if we want to make a trapezoid oblong, since it will still have the same geometric properties in terms of area, is that we could put the 20 on one side. And so that if I go up a height of Y, the extra distance we are increasing is a distance of Y. So our width is just going to be 30 plus Y. And regardless, we should always check ourselves. Of course, if Y is 0, we are at 30. If Y is 20, and then our total width will be 50. Okay, so let's finish up the integral here. Our force now is going to be density times gravity times the integral of dA is our W times dy. Of course, we needed our depth here. So we will have density times gravity, and our width of each one is 30 plus Y. Then we've got the depth, 16 minus y, dy.
Can you show the scratch work above you?
Sure.
Thank you. That's great. Thank you.
Okay, so the end of that then is just where do the bounds lie, right? We want to finish the integral. The water in these slices go from 0 up to 16 relative to our coordinate system. Any questions on that? So that integral, pretty easy to do from there. And again, with a lot of these problems, you'll have these constants given to you. They might give them to you in the problem. I always just keep them out as constants until the very end. If we need to plug in the actual numbers, we can plug them in at the very end. Any questions on that guy? All right, let's take a break for a minute and then we can talk about more of these problems. We need to talk about moments and centers of mass. Okay. So we've got tomorrow to talk about this topic as well, at least part of the day. Tomorrow's going to be a recitation though as well. So our Tuesdays and Thursdays, I gotta kind of balance the time because tomorrow we want to talk about differential equations. So let's do, maybe we'll introduce centers of mass. I don't think we'll have enough time to get through some of these problems. Centers of mass problems are just a pain. Conceptually, I don't think it's too hard. It's just that there's a lot of calculations and a lot of individual calculations you have to do. For a two-dimensional object and computing a center of mass, you have to do 3 different integrals. You have to compute the mass, then you have to compute the moments for each coordinate. So let's start off with pulling up a rope up a side of a building. Find my example here. So let's suppose we have a 200-pound rope. That is 100 feet long. If you want to use the metric system, just think 200 kilogram rope, multiply that times gravity if you want to get a force. 100 meters long. Change the units if you'd like. And it's hanging over the side of a building. So we've got this building. And let's just say we have the rope and it's hanging right at the edge and hanging straight down. So we've got our 100 feet. We want to know, calculating the work, to lift the rope. So you're standing there, pulling that rope up. And so, of course, one of the things to note, we are working against gravity again. So we only have to pull vertically. As soon as I pull up and then pull horizontally, you're not really doing any work pulling the rope horizontally. It's only the vertical motion of the rope that contributes to the work. So we want to ask, how do we want to break this work problem up into smaller pieces? So for this one, I like to do these, again, df times a distance. So force times distance. And by writing that equation there, I've sort of inherently chosen our axis to be a little bit different from what we were doing the last time. So in this case, let's choose our axes, our coordinate frame as our origin here, and actually, let's call this distance x. So it's oriented a little bit differently, kind of sideways, where down is positive x. And how are we going to slice this up? Well, we have an infinitesimally thin piece of rope here of length dx. And this length at dx, we have to move a distance of x. What is the force on this infinitesimal piece of rope? Well, that is our df. How is it broken down in terms of physics laws? So df, force, is going to be the mass times gravity. And the mass, sorry, we actually don't need gravity here. We're using the empirical system, so we don't have this. We can skip a step since we already have force. So the force is just going to be the density, which is the weight density, not the mass density, times the volume times the distance we have to travel to get work. And what is the volume? Well, we're going to consider it an infinitesimal piece of rope. And so volume we could count as, area times thickness. In this case, since we're considering it as a one-dimensional object, the volume is just dx. And to specify, this is going to be our weight density. What is the weight density? We have a 200-pound rope that is 100 feet long. So the density is 2 pounds per foot. So this one's easy enough to compute. Integral of 2x dx. Where are our bounds going to be? So this is something we got to be careful about, right? Because we chose like a weird coordinate system. Our bounds start from here and then go positive x downward. So by the way we chose it, our bounds are going to go from 0 to 100. So computing our total work, going to give us 100 squared, or 10,000. And this is going to be foot-pounds of work. So those are rope problems. Let's get into center of mass. So some of the equations I've been using, I'm not sure how familiar you guys are with them. So maybe we should write a few things down. Is that force against gravity? So our force is mass times acceleration. And then mass is density times volume. That's a Greek letter rho there. So since the density and gravity are almost always constant, this is why I kind of break down the dF is just dm times gravity. dm is just the density times dv. And so our mass, our total mass of a system. And so a priori, what are we doing? We usually have some sort of shape defined by curves, and we'll call it some region R. We often call these two-dimensional objects lamina. And so the mass of this, if we wanted to find the total mass, we're going to integrate. We often generically denote the integral as just the integral over the region R, if we haven't found the bounds and appropriate parameterizations yet. Then mass is the integral of dm. And according to our equations, our dm is going to be rho times dv. So really what we want to do is just integrate over the area. Of course, in this case, we can change it. If you're in two dimensionals, your volume means area. And this will give us the total mass of that shape. Now, sometimes rho is non-constant. In the last problem, what we saw in all the other problems, the density of water is constant. The density of this rope that we had, we assumed was uniform throughout. It wasn't thicker or denser in some places than others. Sometimes with these lamina, you can't have rho as non-constant. So just be careful with that. We can't always pull out rho. If rho is a function of x or a function of y, sometimes you have to keep your rho inside there. So mass, that's one part of finding the center of mass. You do need to find the total mass. And then you also need to find your moments. And this is going to sound counterintuitive with the way we denote them, but our moment about the x-axis is going to be the integral of x, or excuse me, this is why I screwed it up. The moment about the y-axis is going to be x dm. What do we mean by this? So what's happening with these moments? Moments in some sense measure moments of inertia. It's the amount of resistance, so to speak, in terms of rotating about a given axis. So if we have some shape, let me draw a different one here. And this is our R. If I were to rotate this entire shape around the y-axis, some of it would be harder to rotate than others in some sense. Some pieces of this would contribute more to the moment than others, would contribute more to the inertia. right? Think of, you know, spinning a top versus spinning a yo-yo. You're going to get more force the longer the rope, right? The longer the lever arm, the more torque you're going to get, the more angular momentum you're going to get. And so if we're taking a look at a region like this and we slice it up into vertical slices, since we are rotating about the y-axis, that's where that y comes from, what's going to contribute to that, to this overall shape and spinning around this y-axis? Well, it's going to depend on the individual masses as well as their lever arm, the distance they are. So you can kind of think about it, well, if I didn't have a strict shape, if I just had blocks, right? If I had this block, and let's say they were connected by a bar that was massless, and we just had M1 and M2. If I were to rotate this bar now around the x-axis, or excuse me, the y-axis, then again, we are in some sense calculating the torque, the force times the lever arm, or the mass times the lever arm gives us the inertia. And we would just add up the individual moments of inertia for a discrete system if we had individual masses. And so, of course, what do we want to do in Calc 2 sense when we have a continuous shape? Well, we're cutting it up into all these infinitesimal slices, computing each individual slice's contribution to the moment of inertia and adding them all up with our integral. So dm, books, of course, not going to write that. It's going to be x times the density times the area of each slice. Since this is Calc 2, we do want to slice perpendicular to the x-axis. And nicely enough now, since our x is there, we can actually write these as functions of x. Namely, let's get a new picture here. So how we're going to do this, let's draw a more accurate representation of types of functions we're going to see. Namely, it's going to be defined in terms of a function. So we usually have some function that is defining the region. And again, if we are trying to find our moment about the y-axis, we are going to slice. We're slicing actually parallel to that axis, simply because, right, this whole piece, the only thing that contributes, as I was saying, is the distance. So anything that's a fixed distance from the x-axis or from that y-axis will contribute similarly to the moment. And so what is our dA? It's going to be f of x dx. So the height of each bar times the width gives us the area there. Again, oftentimes this rho is a constant, so you can usually pull it out and make the integral simpler, but just be careful. Sometimes it's not. Sometimes rho will give you a different function. Sometimes it gets denser and less dense as you move left and right. So this is our moment about the y-axis. The center of mass, or the x-coordinate of the center of mass, is then just going to be the moment about the y-axis divided by the total mass. And then we should have a density function in here, density and density. And so the nice thing is, at least if density is constant, we can pull that density out of both of those and they will cancel each other out. The y-axis is, excuse me, the x-axis, the moment about the x-axis, finding the y-coordinate of the center of mass. It's a little different. I mean, it is, you can do essentially the same thing in Calc 3. You will learn new techniques to have the same principle in terms of finding it. But for Calc 2, since we can't do double integrals, we have to finagle this a little bit. We still want to, if we're doing all of our integrals with respect to dx, we still want to do this moment about the y-axis, excuse me, moment about the x-axis in terms of x. So we need to, in some sense, replace this y. So what's going to go on with this guy? Well, each of these pieces is our dm. But now we are rotating about the x-axis, right? So instead, the trick we use is that, well, the y, we can kind of think of each of these bars, even though they are bars, and if we are rotating this bar about the x-axis, the weight of the bar at the end is going to contribute a lot more to that moment of inertia than down here. But because the bar is uniform, it's symmetric, we're actually going to just pretend that this bar has all of its mass concentrated right at the middle. So we're just going to approximate that with 1/2 times y. So 1/2 times f of x will give us the center of mass, or excuse me, the vertical center of each bar. And then our dm, once again, is just going to be delta times dA, which is going to be f of x dx. So all in all, the moment about the x-axis is going to be 1/2 times f of x squared dx.
Times rho, or the density.
Times rho. Yeah. Thank you. Times density. And then the y coordinate, center of mass, is going to be mx over m. So this integral divided by your mass integral. So if you understand the concepts, these ones aren't too bad. The way to remember it, I don't like using these moments of y and moments of x again, because they're, we're changing variables and it's easy to just make a brain fart. You kind of just have to think that if you want to find the x coordinate of the center of mass, you want to integrate x times f of x. Y coordinate, y times f of y would give us a nice representation, but since we are doing it in Calc 2 terms, you kind of just have to remember this formula. Just 1/2 f of x squared, and then divide both of those by your mass integral. And so you do have to do a lot of calculations with these. You have to do 3 separate integrals to compute the center of mass. So they can be a little bit lengthy. We'll try to do one tomorrow. Any questions?